So we have Frédéric Simbeli, who received a PhD degree from the Research Institute on Microwave and Optical Communication, XLIM, University of Limoges in 2018. Her research topics include the characterization and modeling of MOS and transistor, and she's currently a modeling engineer in AMCAD engineering. And we also have Nicolas Labrousse, who received a Master of Science degree in high-frequency electrical engineering from Limoges, France in 2005, and a PhD degree from XLIM, also in Limoges in 2009. He has worked for more than 7 years at NXP Semiconductors in Toulouse, France, as a modeling and development engineer. He joined the MCAD engineering as a modeling engineer and smart model project leader in 2020. His main field of interest are compact modeling of transistor devices and nonlinear device characterization. So thank you for giving this talk, and the floor is yours.
Can you hear us and see the slides? Okay.
So, hi everyone, thanks for this introduction, Edmond Piero, and thanks for World Microwave Congress for the invite AMCAD for this Congress and offer the opportunity to present our recent work. So this presentation deals with the pre-RF pulse IV measurements for enhanced transistor compact modeling work, and we will share the presentation between me and Nicolas on different aspects. So the outline of the presentation is the following. Firstly, we will present the characterization and model extraction with a classical approach used at AMCAD. So we will detail the measurement used for model, the modeling extraction flow, the model result also. And after, in the second part, we present the pre-RF pulse IV measurements, so the principles, the bench, the algorithm used to do the measurement, and also some results. And at the end of the presentation, we will describe the model development according to this new measurement approach, the extraction flow, and also some comparison on model and measurements. So the measured and developed model for GaN transistor is a challenging task, in fact, and the process to extract a compact model, a complete compact model, is sequential and incremental. And I will detail all the steps in the next slide. And in fact, the nonlinear behavior of a component is measured and extracted against IV and S parameter measurements. The thermal and traps after the models part are both extracting using a pulse IV measurement in function using different synchronized pulse IV to capture thermal and trap time constant. Once the model, in fact, contains all the effects, it must be also validated against a large signal measurement in a non-50 ohms environment. Then this compact model are used also in circuit simulation software to design. It is also possible to use circuit stability analysis in order to stabilize the circuit, both in small and large signal configuration. And from the compact model, in fact, of the transistor, the key part is a nonlinear output current source. And he determined the DC and the RF transistor performance. In that way, it is a challenging task to develop a complete compact model with a thermal and traps effect. So characterization and modeling work are very time consuming. And to obtain a good model prediction, in fact, it is also necessary to measure the IV characteristic in different conditions to exhibit successively thermal and trapping in effect inherent to the GaN transistor. And specific measurements are realized to determine the traps effect on the IV characteristics and also on the transient response of the components. Today, even if some effort are made to each model step, it is always necessary to through a model refinement phase, and the difference observed between model extracted and the model refined against load pool can be due to the operating condition, which are different from the measurement and the one used to extract the model. And the other possibility is that the measurement used for extraction are not aligned to the characteristics used in large signal performance. So despite a great attention during the model extraction is done, it is not an easy process to align model and measurement with all these effects. So the first part is dedicated to the classical approach used at MCAD. So we will begin to develop and detail the measurement used for model. So firstly, the first step is to perform measurements, IV and pulse S parameter measurements at a certain condition of Gaussian bias, typically 0, because in this condition, we negligate traps and thermal effects. So here you have a representation of how it's worked to perform the measurement. So we choose a certain quiescent level, and all the pulse level are done to represent the complete IV network for different VG and different VD. And for all of these points, we perform combined S parameter measurements. Here it's just a slide to remember what is the model extraction flow in a classical approach. So firstly, we will done the extrinsic parameter extraction with a small signal measurement. In the second time, we do a high-V model, so high-V characteristic with output current source and also input diodes. We used mathematical equation also and extraction to model, in fact, the nonlinear capacitance, so CGS, CGD, and CDS. And after that, once the model, a complete nonlinear model is performed, is created, we can also add some effects, thermal effects and trapping effects. So the part of small signal extraction is done through an optimization, in fact. So you can find in this slide a representation of the extrinsic part and classical topology for transistor. So you can find the inductance, resistance, and capacitance for each axis, gate, drain, and source. And in fact, we begin by set boundaries for each extrinsic parameter. And we can then optimization, tuning, or also used a Cole-FET measurement to have an idea of each value of the extrinsic parts. Once the optimization is done, we can look the fit between S parameter measurement and S parameter from the model and see if we have a good fit. If we have a good fit for one bias point, we can go to 2 points of bias, 3 points, etc., until a multi-bias extraction of the linear model. Just a note, in fact, there is only one set of extrinsic parameter for which intrinsic parameter are frequency independent, like it is demonstrated in these two graphs. So the first step is extract a small signal, so extrinsic parameter. And in the second time, we will take attention on the nonlinear current source. For the moment, the nonlinear current source used at MCAD is based on Tajima equation. And we have a model formulation that allow to predict very accurately the high-V curves and also the partial derivative GM and GD. We have ability in our software to write our own equation. So we can write equation from Engelhoff, ASM, and other kind of model. We can also add some other parameter if we want. And you have also diodes model. So for gate drain and gate source diodes, we can include the equation and have a complete model for diodes also. After that, we take attention and we take time to extract the nonlinear capacitance, because nonlinear capacitance are impact a lot in large signal performance of the components. So we will extract the nonlinear capacitance in function of the fictive load cycle, or also in function of the bias point of the application of each application. So if it's AB application, B, or class C, it's depend of the application. We will change the plot line where the nonlinear capacitance are extracted. So here we demonstrate the methodology. So firstly, we will plot, in fact, the nonlinear capacitance in function of the drain voltage, and we can observe the behavior of the capacitance if it's needed to have 1D or 2D nonlinear capacitance equation. And after that, we will use optimizer or tuning window to extract the parameter of each nonlinear capacitance. So the first step is done. So now we have a nonlinear complete model, but without traps and without thermal effects. So the third step is dedicated to implement, in fact, the thermal effect on the model. This thermal model is divided in two parts. One part is dedicated to the temperature dependence of the nonlinear current source. So for that, we will change the check temperature of the components and measure the IV characteristics. And we can write some nonlinear equation or linear behavior of each parameter of the current source in function of the temperature. So we have, after that, a nonlinear current source depending on the temperature of the check. The other part of the thermal model, of course, is the thermal circuits. So with the thermal impedance, thermal resistance, and thermal capacitance. We can use different methods for extract thermal resistance. So thermal reflectance, Del-Alamo method, or in this case, we just present the coincidence method. In fact, coincidence method is a superposition of two networks, one network in pulse mode for a certain high temperature, and another one in DC mode. And we just superimpose this one network, and for a same VGS, we are able to calculate the dissipated power at the intersection point between the two networks. And thanks to that, we are able to calculate the thermal resistance of the components. And the second part of the thermal circuit is the thermal capacitance. For that, we use our hardware PIV system to measure very long pulse measurements. And in fact, with that, we can see the decrease of the current along the time and determine the different time constants due to thermal aspects. And we can see that when the slope of this decrease change, we have a second or third thermal time constants. And this gives us an information to know the number of RC cells inside the thermal circuit of the model. The traps effects now are separated in two parts also. First for amplitude of traps, and in a second time in transient response, in fact. So firstly, we measure IV characteristics in pulse mode for different quiescent bias. So you have already seen that in the first talk about Professor Rodolphe. And we see here that from different quiescent, in fact, we see the impact of gate traps or drain traps. The first network in blue is at 0, 0, and the second one in red, you can see that we only change, in fact, the quiescent bias for gates. And we see that between blue and red curve, you have a decrease of the current and a variation of the KNI voltage. And the latest network is in green is for a different quiescent bias for drain. And we see now a high decrease, an important decrease of the drain current in function of this quiescent voltage. So we will write some mathematical equation to take into account this decreasance, and variation of this current in function of the quiescent voltage. And also we perform transient measurements. So we also done a long pulse measurement in certain conditions. So when we want to observe gate lag, in fact, we will put the drain voltage in DC mode and pulse the gates, and we can observe the emission process like it is presented in this slide, the emission process due to gate traps. And when we want to observe the drain lag emission and capture, we do a continuous voltage on the gate and we pulse the drain side. And we can observe on these characteristics the capture process during the pulse and the emission process at the end of the pulse. The typical trap circuit is presented also in this slide. So we find some resistance and capacitance to represent the trap time constants, and also a circuit of reshaping that allows us, in fact, to adjust the magnitude of the lag effect. So briefly here, it's a representation of a global model. So you find gate, drain, and source accesses, of course. We found diodes between gate source and gate drain. We found at the middle the nonlinear output current source. We found the three nonlinear capacitance. Before the nonlinear current source, we can see the traps effect circuit. So the trap model circuit is before the nonlinear current source. In fact, to change the gate command that comes and that's through the nonlinear current source. We found also a dissipated power circuit and a thermal circuit. After all this extraction, we can compare the model on all the measurements. So here it's a representation on the IV characteristic at 0, 0. We can find 4 green points on this network. And on these 4 points, we observed the S parameter measurements. Sorry. So here it's a representation of S11 and S22, but of course we compare the S21 and S12. We have also comparison for a network at another check temperature, also 100 degrees here in that case. And the IV characteristics comparison for different quiescent bias points. So the first one is for VP and 40 volts, and the other one is in AB class. AB class is done because a load pool application and large signal application is for this specific bias point. So the aim of this talk also is to present the new method, the new approach used for extract a model. So here it's a comparison like a bench marking, in fact, between a classical approach and the new approach. The motivation, in fact, is that extracting a compact model with all the effects are very long and time consuming and is very complicated to extract for different frequency, different bias, etc. The aim now is to find a solution to extract an accurate model, but very quick. So for that, you used a pre-RF pulse technique. So these techniques will be detailed in the next slide, Nicolas. But here it's just to explain you how it's work and how we spend time to develop a model. So for pre-RF pulse technique, we use also the same kind of measurements without take time to thermal and trap characterization. Why? It's because, in fact, the pre-RF pulse techniques used one measurement in the same condition like a large signal condition. And in that way, when the measurement is performed, in fact, we consider that the thermal and traps effects are like a screenshot, is at a certain established state. And that's why we not implement in this kind of model traps and thermal, because it's already taken into account in the measurements. So in that way, we don't take time to develop thermal and traps model. That's why we can have a certain we reduce the development time of the model. Here we can see that the model from our experiments we done at SAMCAD, we consider a development time reduction around 30%.
Thank you, Frederick. So I will in the next section I will talk about the pre-RF pulse IV measurement principle. Also, I will speak about the measurement bench. How do we process this type of measurement, and to well understand why we developed this methodology. We first need to consider an IV characteristic. In fact, two kinds of IV characteristic. And we need to observe, in fact, what happens when we are measuring, characterizing a transistor with standard pulse IV measurement. Standard pulse IV measurement, so as it has been explained by Frederick, is that you have a quotient bias point, which and from this quotient bias point you will pulse in order to measure the different IV characteristic points here. So in this graph on the left, what I am showing is that I'm showing two kind of IV characteristic. So the blue one is done at 0, 0 quotient bias point, and the black one is done at a given quotient bias point, which is here VP 25 volt. And if we look at the graph on the right, in fact, we just focus on one IV curve, meaning that we are looking at one VGS curve. So in blue, this is the characteristic at 0, 0 quotient bias point, and in red, this is the representation of the characteristic at another quotient bias point. And if we look at the different chronogram for those two curves, in fact, what we can observe is that for the IV characteristic at 0, 0, in fact, we are always pulsing on VDS with upward pulse. Okay, so if we are looking at what happens, in fact, during this measurement, when we are measuring the current, in fact, we are always measuring during the capture phase. And for some of the systems that we use, the pulse widths may be lower than the time capture, meaning that, in fact, when we are measuring the current in these cases, in fact, we are not able to see the capture time constant. We are always measuring before the capture time constant. At the contrary, if we look at the IV characteristic at a different quotient bias point, now we have different cases. We will have a case, for example, when we are pulsing upward in VDS, where we will measure, in this case, also during the capture phase. And this is why the two IV characteristics are achieving the same current during for this part of the IV network. But when we are pulsing downward, in fact, so when we are applying a VDS pulse, which is lower than the quiescent voltage, now we are measuring during the emission, and the emission time constant is much longer than the pulse width, and this is why we observe a decrease in the current. So what does it mean when we have that kind of characteristic? That this is why we represented, in fact, two areas in red and in blue. Is that meaning that for the area, the part in blue, in fact, the trap charge state, I would say, will be driven, in fact, by the pulse itself, the pulse level itself. And however, in the red area, in fact, the charge trap state will be driven by, in fact, the quiescent level. So this can be a problem if we try to fix the trapping state of charge. And this is why, in fact, a new system has been shown and developed, which is called the double pulse measurement. So here we are talking about double pulse IV measurement. So here it's a representation of how it works. So we have a chronogram here, where we show at the top the drain voltage and at the bottom the gate voltage. And in fact, we have different sequences. So here we have the IV characteristic, which is represented, and we can see on the chronogram the different steps where, in fact, the pulse are going. So there is a pre-pulse, a DC pre-pulse. So we start at quiescent bias point, and right after the quiescent bias point, we apply a DC pre-pulse, and this DC pre-pulse typically goes where the traps effect are higher, which means when we have a high VDS voltage and a very negative VGS voltage. In this condition, the traps effect are maximized. And right after this pulse, we apply a second pulse, which is the B point here in this IV characteristic. And this one is where we are measuring the current. So the interest of that is within this technique, we are able to fix the trapping state of charge in the whole IV network. So this has been demonstrated in this paper, in fact, where we can see the drain voltage and with the different with and without the pre-DC pulse. And so we have two kinds of characteristics which are shown in this paper. On the top, this is a two IV network which are measured at two quiescent bias points. So without a pre-pulse. Okay, so as we can see, for the two different quiescent points, there is a difference in the IV network, and this is exactly what we observed in our previous measurement. It's because, in fact, by changing the quiescent bias point, you will change the trapping state of charge. And by applying now the pre-DC pulse, the measurement is called isodynamic because, in fact, either we change the quiescent bias point, now the two characteristics exhibit the same output current because we are fixing the trapping state of charge. So this technique is very interesting in order to have an isodynamic characteristic. But there is another effect that we need also to take into account when we are doing compact modeling, is the effect of RF signal. How the RF signal impact traps. To illustrate that, here what we are showing, that we are showing the output current characteristic in a function of the input power. And we have two kinds of characteristics. The red one is with traps effect, and the blue is without traps effect. It's just to illustrate that with traps effect. When we start to increase the input power, we'll start to see a decrease in the current characteristic due to traps. In fact, if we look at the IV characteristic, we can plot for each input power level different kind of load cycle. So here, as we are at a very low power level, we are close to the quotient bias point, and so we have a very small RF swing. So we have almost no traps induced by RF signal. And as far as we increase the input power level, then we will start to see different load cycle, and this load cycle will impact traps. So in fact, what this comparison shows is that there are variable trapping effects that are induced by the RF signal. So in our pre-RF pulse measurement, we try to, in fact, to emulate this phenomena. And to do that, what we do is that we'll use a combination of pre-RF pulse and DC pulse. So this is shown here in this schematic, where we are representing so the transistor here, and we have RF source, RF pulse source at the input. That from which we'll apply so the pre-RF pulse. At the output, we have the load, so that the transistor will be loaded by a given impedance that we can change. And we have a standard pulse IV system, and that we are combining those two signals at the axis of the transistor. And so if we look at the gate axis, we'll have the pre-RF pulse to be able to set the trapping effect. And right after this RF signal, we'll have the pulse IV measurement. So we are doing this at the input and at the output of the transistor. And within this system, we are able to to vary first the pre-RF pulse level, so to vary the trapping state of charge, and also to change the load impedance, and to be able to be as close as possible as the final application. So combined to this measurement setup, we have a specific measurement algorithm. So here it's a representation of an IV network, so we can see output characteristic versus output voltage. And we also here have the output characteristic upon input gate voltage. So what we do is, in order to be able to vary the trapping state of charge, we will apply different pre-RF pulse level. As far as we are going far and far away from the quotient bias point, we will change the pre-RF pulse level. So here, as an illustration, we show three different pulse levels. So when we have a low pulse level, we will be close to the quotient bias point, so in green. And we will measure all the DC IV in this area. And in another area, when we'll go far and far away from the quotient bias point, we'll apply an higher input RF signal, and we'll have on the full characteristic at the end the highest RF input signal, so that we'll be able to have dynamic evolution of traps during the measurement. So the main interest of that is to compare, for example, to a basic double pulse IV measurements that I presented before. Is that in the basic double pulse IV measurement, we have a fixed pre-DC pulse, so that the IV characteristic will be representative of this trapping state of charge. With pre-RF pulse measurement, we will vary the RF signal according to to the large signal. And so we'll have, during the IV characteristic, a dynamic variation of traps. So this will be more representative when we will compare the model, when we will compare the model against large signal measurement. So the procedure of the measurement is in 3 steps. So first, we are doing a preliminary load pool measurement. So like this, we have a load pool pattern here. This measurement, in fact, is used for model validation, and it is also used for calibrating the pre-RF pulse. So to calibrate the pre-RF pulse, what we do is we calculate the input and output RF amplitude of the RF signal based on incident and reflective wave during the load pool measurement. And based on that, we're able to know, in fact, what are the variation between the input power that we can see here on the x-axis on this graph, and the magnitude of input voltage. Okay, so here we are able to link for each power level a given RF amplitude at the input and also at the output. So in the second graph here, I am showing the result of the variation law versus the input voltage on the y-axis and the output voltage on the x-axis. So this is a normal process, I would say, when we increase the input power. By the way, both input and output RF amplitude are increasing. So by selecting, this pre-RF pulse IV variation law depends on the load impedance. So for each load impedance that we will select during the load pool measurement, we'll have a different load pool IV variation law. And at the end, we are using this pre-RF pulse variation to be able to discretize, in fact, the IV network, and to say for each area of the IV network, I will have a different pre-RF pulse level. So these are some results that we obtained for on the measurement of GaN-empt transistor. It's 8 gate finger with 50 gate widths, 50 micron gate width. Sorry. So here it's a comparison of the result of IV network without double pulse with basic double pulse measurement. So the pre-DC pulse measurement and the pre-RF pulse measurement. So what we can see is at very low power level, so close to the quiescent level, we are close. So without double pulse and with the pre-RF pulse, we achieve the same result. This is normal because at this point, in fact, the RF signal of the pre-RF pulse is low, and we are close to the measurement without RF pulse. However, when we compare this with the measurement done with pre-DC pulse, we can see that the traps are overestimated in that case. If we now look at higher VGS characteristic, what we can see is that now the comparison between the basic double pulse and pre-RF pulse measurement achieve almost the same current, whereas without double pulse trapping, we are underestimating traps and we are getting higher current. So just to say that within this technique, we are able to have a dynamic effect of traps, and this dynamic effect is applied by the pre-RF pulse and it's more it will follow, in fact, the RF signal envelope that we have during the load pole measurement. Recently, we also improve a little bit this algorithm, because in the first case, what I've shown is that we were taking the maximum voltage input and output voltage amplitude. And now we are also considering the real load cycle. So the principle is the same, except that we are discretizing now, measuring IV characteristic, IV point, on the same path as the load cycle, meaning that we are now taking into account the real path of the RF signal in order to measure the IV characteristic. This is how it's done. So I just take one load cycle. So in fact, what we are showing here is that it's the amplitude at the input, so at the gate, and here is the amplitude, the RF amplitude at the output. And in fact, we are now taking into account the phase of the input and output signal in order to be able to acquire the output current during the load cycle of the RF signal. These are some results that we obtained recently. So the extraction has been done at the 3 load impedances, so which are named A, B, and C here. So A, it's the load impedance which achieved the maximum output power. B is a characteristic which shows the highest current drop versus the input power. And the C point is the maximum efficiency. So here is the representation of the IV characteristic. So plot within the load lines that we have, the load cycle, in fact, we have. So for maximum output power, as we can see, the load cycle are going at very high VGS, but they are not the swing in output voltage is less important that we have for the other measurements. Here for the maximum in current, as we can see, the load cycle goes in a very it goes to the knee, in fact, area of the IV characteristic. As we can see here, we have a big drop in current when we have high pre-ref pulse measurement. And the third characteristic, it's at maximum efficiency. And as we can see also, we have, again, a different IV characteristic. So the aim now is to be able to take into account those 3 IV characteristics to model it and to incorporate this in the model.
So the last part of the presentation is dedicated to the model development according to this new measurement methodology. So here it's compared to the first extraction flow. This is a new extraction flow. So firstly, we will use S parameter in the AB class to extract classical extrinsic parameter, like in the first method. We used optimization algorithm and multi-bias extraction. So the first step is identical to the first one methodology. The second step varies because now for IV network, we have the measured characteristic from the pre-RF pulse measurements. So like Nicolas said, we have this measurement for free load impedance, free specific load impedance. And we see from the measurement result in the previous slide, we have IV networks, and all the points of this IV network are different in terms of VG and VD. So we have post-processed this data in order to fix the VGS. So we've done interpolation to have now IV characteristics, like we have some habits to see it, in fact, so with fixed VGS. And it is better to optimization of the nonlinear current source also. So after that, after this post-process, we do optimization of each parameter of the nonlinear current source for each load impedance. To be noted that for this new nonlinear current source, we had some mathematical equation with hyperbolic tangents because we observe some bump behavior inside the IV characteristics due to traps, and it's needed to take into account to have an accurate model in comparison in large-scale simulation. After this optimization, we have a parametric model development in function of the load impedance. So we have implement equation to be able to have a model that works for the free load impedance. And the last step is a IV model comparison on IV characteristics and on load pool validation measurement also. So here is the first part for model comparison. So the model comparison is done here for the maximum efficiency impedance. So the two graphics are for the same load impedance, but you can see at left the raw data, in fact, so directly measured with the pre-RF pulse techniques. And at the right of the screen, you can see the graphics that is post-process. So with fixed VGS. So this view is more classical, and we can observe the bump behavior, as I said before, for a certain range, in fact, of VGS. For this device is around -3.5 to -2.5, and we observe this variation on the current and this bump. That's why we added some equation on this to be able to reproduce this behavior. And we had it also on this comparison between model and measurements, a load cycle comparison given at an input power level around 10 dBm. And has to note that for this input power level, in fact, we are in the shape of the average output current. We are in the deep behavior due to traps. So this load cycle comparison is very important because we see at this step that we are able to reproduce the trap effect on the characteristics. So here it is a model comparison for the two others load impedance, so maximum bump load impedance and also maximum output power impedance. We see on the graphic at left a more pronounced trapped effect, in fact, for this impedance. That's why we name this impedance bump, more bump, because we see that the bump inside the IV characteristics is more pronounced and also is a delay in function of VGS and also in function of VDS. We see a shift of this bump. And we have implement a mathematical formulation, and the model is now able to switch, in fact, between the load impedance for this free load impedance. Here it is a model comparison, but now in large signal condition. So you can see the main RF characteristics of the components. So input reflection coefficients, output power, power gain, efficiency, and also average output current. And you can observe that for the free case, free load impedance, we have an accurate prediction of the model in function of the measurements. So to conclude on this presentation, the technique presented in this presentation make it possible to obtain, in fact, a realistic IV measurements by considering both effect of traps and thermal effects close to the final application. Such IV characteristics provide some information to extract the model and particularly the nonlinear current source. And it allows a better prediction of the impact of traps on the final performance for this particular application. Without additional traps model, And this patented technology, this patented new measurement used a classical VNA-based load pool bench. And the measurement condition used for model extraction, reducing the number of model iterations to fit the model on small and large signal measurements. And thanks to the time benchmarking we present before, we observe that the measurement with this new method reduce the back and forth optimization process. Thank you for your attention.
Thank you. Do not hesitate if you have any question. We put on this last slide the different modules that are necessary for these techniques implemented in IVCAD, and also some documentation and some videos related to that work.
Thank you for your very extensive presentation. It looks like a very nice framework. You have already some questions asked in the Q&A tab. If you are able to find it, and if you may want to reply to a few questions, although we are really tight in timing, so please maybe answer the first couple of 2 questions, and then you can directly reply typing the reply if you can. Thank you.
Okay.
So the first question is regarding the gain. No, I think it's so the gain increasing is power.
Yeah, on slide.
On slide 15. Back. Sorry, it's a little bit.
Oh yes, it's depend. In fact, the gain increasing in function of the power. It's depend of the class of operation and the impedance. So here, typically, I think it's a bias point a low current. So that's why in function of the power it increase. Different layout. You would like to say different scale or different or dispersion between some device? I don't know. If it's a scalable model, in fact, you need to implement scalable scaling equation in your model. And if you talk about the dispersion between the component, in fact, on a wafer, on a complete wafer, for example, you need to do some dispersion measurement. In our process, you perform measurements, IV characteristic parameter measurements on the entire wafer to determine what are the median sample, and we extract a model on this median sample.
So you will be able to do a standard scaling, up and down scaling, because you are still able to scale up or down your IV characteristics or your capacitances. So this does not change from the standard process. The only difference is that we are now considering the real condition of the final application, so the bias point as well as the frequency of operation. For the next question, yes, so typically when we do a measurement like pulse IV and S parameter measurement, we are with timing which are less than 1 microsecond, and this is also one of the fact that we have some discrepancy between the small signal measurement and the large signal measurement. When you do large signal measurement, you have additional equipments like tuners, for example, couplers that will, in fact, make the IV characteristic different. In order to be in the steady state to measure the IV current, you will need to increase that pulse width. And so typically for a load pool measurement, 4 microseconds is can be a standard for load pool measurement. The thing is that your having a much more thermal effect. But with this technique, in fact, these are embedded during the load pool measurements, and we are taking this into account with our modeling process. Any thoughts on the harmonic loads effect? Yes, so this is some work that we start to do. In fact, we are going through another experiment using that technique in order to better correlate with load, with harmonic influence on the results. So in fact, yeah, this work will be soon uploaded. In fact, with now taking into account the harmonic the harmonic on the load.
Yes, but the first experimentation on it demonstrates that the extraction, the optimization of the nonlinear current source, the determination of the parameter, in fact, of the current source, are not very impacted due to the harmonics. But we consider now we do more in deep on this job on it, so we will validate that and produce some result on it.
So the next.
Okay, so I suggest that you may follow up by typing the reply to the next couple of questions that you have.
Okay.
So thanks again for your very interesting talk.